Guys, so today I'm going to talk about molar gas volume and how to calculate the molar gas volume if you are working with a non-ideal gas at standard temperature and pressure. So just before we jump into calculations, I quickly want to show you this interactive exploration of gases with pressures and temperatures and how each of these variables change with one another. And we're not going to go into too much theory, but I just want to show you the principle of what happens if you have a certain amount of molecules. You can see the more molecules I add to my container, the more pressure I put into the system. And now remember, what's happening is that these molecules are colliding with each other and colliding with the walls of the container, exerting a force onto the container, and therefore you see an increase in pressure as that happens. You can then also now go and say, well, I can increase my temperature, and the higher the temperature, the higher the kinetic energy of these molecules will become. And so therefore, if I increase the temperature even more, you will see that the velocity of the particles will increase, and therefore the kinetic energy will increase, and you can see how the pressure will then also increase. So there's a direct relationship between the temperature increase and the pressure increase. Okay, more temperature added, more collisions, and higher kinetic energy. Now, how does this change in terms of the volume? So pressure and volume is inversely proportional to one another. So if I go and I enlarge the volume, decrease. Okay, so you're basically alleviating the pressure of the collisions and less molecules that interact with the walls of the container. So exerting. What happens if I have this large container and I go and I cool it down a bit? So what's going to happen is the molecules will move slower and slower and slower, and therefore they will exert less collisions on the surface of the wall, and you will see that the pressure will keep on decreasing. So as you decrease the temperature, your pressure then also decreases. So it's really nice for you to just try and see when you change the different variables, make the volume smaller, you can see how the pressure now increases rapidly, and there's high kinetic energy, higher temperature, and therefore more collisions being exerted on the wall of the container. And if you open up the container, you'll see the molecules escaping from the container, and therefore the pressure drops again. So it's really interesting just to observe how the variables change and to understand the relationships between volume, pressure, and temperature. Okay, we'll explain that in more detail in a different lecture series. So let's go to our calculations. Okay, so let's quickly look at this question. What volume of SO3 will form if 30 cube decimeters of oxygen reacts completely at Stp? So what is Stp? That's important. And what is the information that they give you? First of all, they tell you that you want to go calculate the volume of this that will form if you have 30 cubed decimeters of oxygen. They also tell you that it reacts completely, which means that your oxygen is your limited reagent, right? It's going to react completely. So STP stands for standard, temperature, and pressure. And it's a set of conditions that we define as standard in the laboratory. So standard temperature is 273 Kelvin or 0 degrees Celsius, and standard pressure is at 1 atmosphere or at 101.3 kilopascals. Okay, so that is standard conditions. So this is standard pressure and that is standard temperatures. So whenever you see a question that asks you about STP, you need to always have this formula in mind. Volume is equal to the moles times the molar volume. And the molar volume represents the volume that 1 mole of a certain gas occupy. And 1 mole of a certain gas will occupy the following volume, and this is a constant. Okay, there's the units, cube decimeters per mole. That's the units of molar volume. So it's the amount of volume that 1 mole will occupy. And now we can go further and say we can now solve this equation with the information that we have. If you ever get a question, and we'll look at those questions later on, where we refer to an ideal gas, then we will use the equation PV equals nRT. Okay, but we're not going to discuss that in detail today. So let's look at this equation. The first thing that should always come to mind whenever you are starting with geometry, not geometry, with stoichiometry, is that you need to always balance your chemical equation. So you need to look at the molar ratios. So let's start with the balancing. So I've got 1 sulfur on this side, and I've got 4 oxygens. So I'm just going to write that down for myself. And 4 oxygens on that side. I've got 1 sulfur on this side, and I've got 3 oxygens on this side. So we need to do something in order to balance our equation, because at this stage you can see this side and this side is definitely not balanced. So you can change something on the one side and see how it alters the other side. So I'm just going to start by putting maybe a 2 there. If I put a 2 in front of my sulfur, then I have 2 sulfurs. Now I have 4 plus 2, which is 6 oxygens. And now you can see you have 6 oxygens on this side, but only 3 on this side. So if I can put a 2 over there, then I can make my 6 oxygens. 2 times sulfur is 2 sulfurs, 2 times 3 is 6 oxygens. And now you have your balanced reaction equation. So first things first, work with the limited reagent. Okay, that's very important. So we are going to calculate the moles. So volume equals moles times molar volume. You have the volume that has been given to you. Okay, remember to make sure that your units are correct. You want to calculate the moles, and the molar volume is given as 22.4 cube decimeters per mole. So you can see that when you calculate the mole, remember, cube decimeters divided by cube decimeters will cancel out, and you will have a mole remaining. Let me write that out. Divided by 22.4 cube decimeters per mole. So 30 divided by 22.4, that will give you 1.34. And you will see that the decimeters will cancel, and you will have 1 over mole, right? So you are now going to bring that to the top, and that's going to become units of mole, and that's why we have the 1.34 moles. So now you have the moles of your oxygen. Now we can do a mole to mole ratio comparison between oxygen gas and SO3 gas. And you will see that we have a 1 in front of the oxygen. I'm referring to this number in front of the molecule. And I have a 2 there. So the mole ratio is 1 to 2. Okay, that's the mole ratio. That's really important. Now that you have your mole ratio, and you know that the moles here is 1.34 moles, you want to work out what is the moles of your SO3. And from simple and basic mathematics, you know that if you have X and you have a ratio, you can, when you go across, you times, and when you go sideways, you divide. Okay? So in other words, you will say 1.34 times 2, right? Divided by 1. And that will give us X. That will give us the number of moles here. And if you just want to be quite simple about it, here's 1. 1 is 1.34, so 2 will be 2 times that. Okay, that makes it actually quite simple. So 2 times that will give you the moles of SO3, and that will give you 2.68 moles. So now you have the moles of your SO3 gas. But do you have the volume? No, and that is what you now need to go and calculate. So I'm going to use the same equation. The volume of SO3 equals to the moles times the molar volume. So now you have the moles, and the molar volume is given as a constant. And you can even put in your units if you want to. But if you work this out, you times that to each other, you get 60 cubed decimeters. Okay, let me just write out the units. Remember, moles times that by the units of this is cubed mole, so they cancel out and you are left with 60 cubed decimeters. And now you've answered the first question. So you worked out volume of your SO3. Now the second question is, what is the grams of SO3 produced? Okay, and from your simple mole equation, moles is equal to the mass divided by the molar mass. So we have the moles, we have the molar mass, and now we can work out what is the mass. Okay, so the moles is what we calculated as 2.68. The mass is what we want, and the molar mass we can obtain from the periodic table. So the molar mass of sulfur is 32, and we have 3 oxygens, and the molar mass of 1 oxygen is 16, so I'm going to times that by 3. And then I can say the mass is going to be that times that. Okay, and if you go and work that out, you will see it gives you 214.4 grams. Okay, so now you calculated the mass of the SO3 as well as the volume with using the standard temperature and pressure conditions and the formula V equals moles times the molar volume, which is a constant. So it's always important to remember when you get your equation, you need to make sure that it is balanced, and then you can do a mole ratio between the substances that you want to work with, making sure that you always choose to work with the moles of the limited reagent. So I hope that was useful. In the next video, I will be working with concentration and how to calculate the concentration for certain solutions. Have a great day and see you for the next video.